はい。 Account 1 thing.
And today we will this final quiz. And then next week, hopefully we'll finish the slides today. Next week we'll have the final tutorial. Second, tutorial, we'll show you know, discuss. So we'll be reach the section. Any questions? Last one. Okay. Okay, today we will go into the last topic of this semester, the Boolean algebra. So this is what we started with. We started with proposition, right? So proposition is one of the Boolean. And then set theory. And then surprisingly, lattice is also a Boolean algebra. So what's a Boolean algebra? It is a set. So there are two operations on it, two binary operations. So usually we call it up or cat. Or sometimes we will write multiply. Okay. So two operations. And then contain two elements, 0 and 1. One more operation called the bar operation. It's a unary operation. Okay. So you should think of in proposition, you should take the conjunction of the proposition or the disjunction of the proposition, and then G, the contribution, and also the true. Right. Set theory, we have the set intersection, set union, and the empty set, the union set. It's five ingredient here, such that another five laws for. So the first law is the identity law. X cut with 0, you get X. X cut with 1, you also get X. So this is the identity law. If you cut with the complement, you get 1. If you cut with the complement, so you should think of it as the P or not P is the tautology. P and not P is the contradiction. You should keep those examples in your mind. And next, you have the associativity. And also the associativity on the cat operation. Right first, or you get the left first. Next, it commutes, so x or x cat y is the same as s cat x, or s cat y is the same as x y cat x. So they commute. And the last one is the distribute. So x or y cut x, that is equal to x cut y, that x cut z. Or x tab y cut z is equal to x tab y x z. Okay, so this is the distributive. So associative is between the same operation, but associative distributive is between two different. For example of Boolean algebra, like what I said, first is the propositional logic. So you need the 5 ingredient, right? So the 5 ingredient, the 0, 1, the 0 would be the true segment 1, point PQRX, and so on. And you can take the disjunction, conjunction or disjunction, conjunction of the propositions. You also can take the disjunction of the proposition again. And then you can take the complement of the proposition. Not complement, the negation of the proposition. Okay. And then last time we also showed that they satisfy this property. This is what we did in the first lecture, first few lectures. And then second, we have set theory. So in set theory, 0 will be the empty set. And then 1 will be the universal set. Okay. And then we consider different sets, maybe for A, B, C. Okay. And then we can take union of set, we can take intersection of set, we can take complement of set. Also, remember the big table that you always ask me to memorize one. Okay, so they satisfy this condition. Okay. Surprisingly, the lattice is also because the lattice we learn from the partial order of. So if I give you 2 lattice points, what do you think? How can you produce another lattice point? If I gave you 2 lattice points, how you produce another lattice point? What operation can you? Let's say you take the skip here. So if I give you 2 lattice points, how you produce another lattice point? It's something we learned before. You have a partial order. Give you 2 lattice points, how to produce another lattice point? What do you do? With partial order. Any way to produce what's the definition of lattice? Definition of lattice. And today go quiz on definition of lattice. Every pair of element has a least upper bound or a greatest lower bound. Okay, so one way is you take 2 points, you go and find their greatest lower bound, or you go and find their lowest upper bound. Okay. So in this case, the 0 will be the least element, and then 1 will be the greatest element. Okay. We will not show how this define the lattice. You can try it. I think it's in the test. So the complement will be those lattice points that satisfy the identity laws. Okay, and then you should check that with this definition here, this 5 law applies. Okay, so that it will define a Boolean algebra. Okay. So let me remind you this table again. So this is what the Boolean algebra will satisfy. But we can see that we only need 5 of the laws to define Boolean algebra. So how about the other laws? So apparently the other laws can be derived from the only 5 laws. So we have abstract the idea of proposition set theorem. As long as these algebras satisfy the 5 laws, we have all these identity satisfied. Okay. So next week, the question we will try to prove some of these laws just using the 5 laws. So this is the power of the algebra. We don't need to care about propositions. We don't need to care about set or so on. We just need the algebra structure. Okay, next. Next, we will look at the function that takes the Boolean uh, variable. Okay, so let's look at the set 0 and 1. Then we introduce d to the power n, the n tuples of b. This AI should be element of b, so that just 0 or 1, string of 0 or 1. So Bn is the set of all possible n tuples of 0 and 1. Okay. So next, so we will call a variable x a Boolean variable if the variable take values 0 or so something is a Boolean variable if it takes value 0 value in b. Next, so a function from En of degree n. So this function only will split out 0 or 1 from Bn to n. Next, we will define Boolean expression. So Boolean expressions, the variable x1 to xn are defined recursively using 0, 1, and first we declare that 0, 1, x1 up to xn are Boolean expression. And we can take, if they are Boolean expression, then we can take the complement of the product of them and the sum of them. So we can start with the Boolean expression and then take the complement, or you can take the uh, sum product, or you can take the sum or Boolean expression. And so let's see some examples. So for example, for xy, x plus y, x plus y plus 0, or x plus y times 1. Okay, these are all Boolean expressions. And so So you can see that actually this Boolean expression define a function. See why this Boolean expression represent a function. Can you see why they define a function? For example, if fx y equal to xy, okay, then you can form the truth table. So if you put 1, 0, what do you get? 0, 1, what do you get? 0, 0, what do you get? 1, 1, 1. So an expression will define a function. Okay. So you can see that we can take sum of expression, product of expression, complement of expression. Okay. So are we getting a Boolean algebra again? Huh? Yeah. So you can ask this question. So actually, we actually are getting a Boolean algebra, Boolean function. Okay. So the function will form a Boolean algebra again. So we can take Boolean sum of Boolean function. So we can take Boolean sum of Boolean function. We can take Boolean functions. We also can take complement. Of course, you still need to check whether they satisfy the 5 rules. Okay. Okay. So okay, let's go into it. Define this Boolean algebra. Yeah. Does it making sense? Make sense. Okay. 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 Uh, yeah. So before that, we will talk about see that when are two function equals. Okay. So normally when are two function equals? When are two functions are equal? When the two functions are equal. When the two functions are equal. Logic? No, I mean normal function.
Then domain temporary. Then
For every domain, they get sent to the same image. Okay. So they agree on the image. Okay. Similarly, for Boolean function, two Boolean functions are equal if they for all the so for example here, right, let's look at this example. X plus y, x plus y times z bar, and g x y z equals to x plus y z plus x y bar z bar plus x bar y z bar. Okay, so the claim is these two functions are the same. Okay, so why are they the same? We can see from the truth table. So that's large enough. Okay, so you can compute the truth table for f. Okay. So if you compute a truth table for f, this is the result. Okay. And then you can see that this one appears exactly on this term. Okay. So for example, if you take x, y, and z bar, okay, y, x, and z bar, meaning this line with this column here, and then the only place you get one is this. And then you similarly you compute y bar and x bar, you will see that the only place they appear is this one and this one. So this f function here is the sum of these three terms. Here, this table didn't produce column for these two, but you can try it. Yeah. Yeah. Any question for this? I see one blocking here. Okay, so you should produce truth G, okay, and then compare the two. So the claim is Z equals to F. Yeah. Any question? Yeah. Okay. So try to produce the truth table of G and then compare the two truth table here. And then you'll see that they are equal on the image. Yeah. But one quick way to see it is this one here is produced by these three. But if you can't see it, you should try to produce the truth table for G. And then you'll see that they will have the same image. Okay. You cannot directly see from the algebra because if you expand this algebra here, you only have two terms. Unless you need to apply more operation. But it's not a directly from F to G. You need to apply some laws. So so in this case here, there's a name for this G. This G is called the sum of product, sum of expansion. Okay. So this is in the 3.2 in the textbook. So that okay. So G is called the sum of products expansion of F because you can see that these are products, and then you are taking sum of them. So sum of products expansion of F. Okay. Next is we'll talk about Boolean expression. So two different Boolean expression that represent the same function then the same function is called equivalent. Are called So, for example, what are equivalent? So xy plus 0 and xy times 1. Okay, so these are all equivalent. They are the same function. Okay, next. So next is the complement of that. Okay. So how do you take a complement of a function? So how do you take the complement of function? So you just take the complement of the Boolean expression of the function. Okay. Show you what does it mean. Okay. So for example, if fxy is equal to x1, okay, then if you take the complement of the function, it will become, so you just take the complement of the Boolean expression. Take the complement of the function. Okay, next. Next, if you have two Boolean function, so like what we said just now, we can take the sum, and take the product. So how do you take the sum or the product of two functions? So functions are defined by the Boolean expression. So you just take the sum or the product of the Boolean expression. So f plus g, the function, is defined by just taking the sum of individual function. So the product, just take the individual or equivalently the product of the Boolean expression. Okay. So with this, you should be able to check that it satisfies the 5 laws and then it forms a Boolean algebra. So next, okay. If any question, you just stop me here. Okay, 7.2. So next, we so last time in propositional logic, we briefly talked about it. Something like this logic. So it's actually used to model the circuit. And the basic element of this circuit are called the gate. Basic elements of circuit are called the gate. Gate. So recall what gate we had last time. We have the inverter gate, OR gate, and the AND gate. So the inverter gate produce P, we produce not P, right? Okay. So in general, if you input X, we get the complement of X. OR gate, if you input xy, you will get x plus y. And AND gate, you will get x times y. So let's just recall what we had last time. And next,
So there are two examples here, but they all produce the same circuit. So both of them are xy plus x bar y. Okay. But there are two ways to draw it. Okay. So, but which way uses the fewer element? Okay. So I think this one uses the less fewer element. Okay. This element. Okay. But this one you need to have 4 input. So the next part of the story will be how to minimize circuit. Okay. Use as few gate as possible. Minimize the circuit. So example would be more example. So you see that the circuit can get as complex as possible. Consider the main function. Okay. So you can read about examples in your textbook, and there's that 3.4, there's something called the errors. You can read. Seng is also doesn't include this one, but you can read on your. Okay. Any question? Any question on this logic gate and Boolean algebra? So Boolean algebra is an abstraction of a proposition, logic, set theory, and at this point. Any question? So from Boolean algebra, we can build a Boolean function. So you can see that this logic gate, all these logic gates are also Boolean function. So these are like, let's say, the concrete form of the function, right? So if you input this value, you get this output. So this is actually a Boolean function. Okay. So this function is realized by gates, by logic gates. So these are all function, different functions. Okay. Then next step, we will try to minimize this function using less gate as possible to reach the same point. Okay. So these are all functions realized by gate. No question. Let's take the break until 9:15. Then we'll come back for minimization.
哎，这个因为看你的
那个
有一个讲，就两个 f，这个关于 f 的 function 和关于 y 的 function 相等，是这个
啊，对，
这个就比较它们的 true table 就可以了，是不是？
比较直接，对，对对
这个里面的 x1和 x2就是对应的01吗？这个
对对，它可以
这个
取0或取1。
哦，OK，那个还有一个，在这个下面还有个对啊。还有一个相等是哪来着？
哦，这个
有一个相等，还有
这个对 f
啊，对
这个对
expression，
，yeah，
这俩有啥区别吗？
这个是我不知道，感觉他用字有点用的很怪。我觉得这个应该叫 equivalent，这个应该叫 equal，因为这个是怎么说呢？
这个是 function，这个是
对，这
function，
是 function，对
这个是表达式嘛
啊，对对
，expression
对。
啊，那我差不多理解了。
呀，
OK，
哎，你不翻看反，
这个意思，对吧？
哎，这个
就是在那个 GLC 那个部分，我不太记得是哪里的知识了。
哦，那个是那个 partial order，之前，在那个，我不知道你没有
是第几课的？
第十的，在你的第九、第八，
就是 relation 那课是吧？
对，在结尾头了，然后结束，对，最后一页结束的时候，有吗？没有了。
这后面就说的那个这个方式。
哎，OK，可以，听着啊，你没有了，
我去看一下那个课件。
啊，对，在最后一个 slide 那里，我记得，我最后一个 lattice definition，你找到的你就会看到的。
两个相乘的话，两个波粒方式相乘的话，那个 x 是什么意思？是在哪儿？看不到。
再说一次，
就是两个波粒方式相乘嘛。
啊，然后
那个乘开之后，他们不是有一个 f 对，就是他们这个 x 代表的是什么呀？
你说
因为我的理解，
这个代表什么？
对，因为我的理解是他们两个不都有自己的那个 variable，
对，
我
你说，
这个 x 的话是哪个？
就是depend 哦，depend 它长成怎么样？比如说 f 如果长成这样的话，g 可能长成这样的话，那这个东西就变成x y 这样子。对，
我想错了，原来是，
嗯，
我本来想的是，因为后边讲电路的我明白了，这个因为前面没讲电路嘛，不是前面没讲，就是前面只讲这个，我就以为这个是他们自己各自的这个未知数，所以我就比较疑惑这个符号里边是指哪个 f 或者 g 的未知数，原来它其实好像不太一样，是波粒未知数啊，所以它就只是一个相当于代数的位置，而不是说具体的字母。
你是说 evaluate 符号啊？你就是说取了一个值，
对，我本来想到可能取值，但是好像现在不是取值，只是这个位置而已，对吧？
你可以说取值也是一样的，就是如果你要取这个的值，你就是要这个先取这个情况。
我明白。
哎，你叫什么名啊？
也叫刘少飞，
刘少飞，少飞，
少飞，飞机的飞。
哎，yes 啊，
一闪四，闪四飞，还有大五这个。
说我漏了，
没有，我在确定是不是有。
为什么问题？有听吗？
是
okay, that's greater than。来，我看一下我的。 真的是少了。对，
是有反射啊。
要。OK，我会改一下。OK，Thank you 啊。
就这个
说
这个图有 list，还有
有
就是它是 lattice。
对，没错。
找这个的话，就是先找它的 list 还有 upper bound。
你要每一个都找到它的 list 和它的greatest lower，每两个 every pair。
那所以 this lower bound 是可以有多的，
不可以，它只有一个吧？最少啊，最小。
greatest lower bound least upper bound。
两个都只有一个吧？每一个 pair 就有一个吧？
配要是两对，就是这样子对。
啊，随便两个，比如说这两个 ，the greatest lower bound 就是这个咯 ，least upper bound 就是greatest lower bound 是下面这个 least lower bound，
least upper bound。
least upper bound 是上面这个，呀，它是unique 的咯，它只有一个吧，所以它 well defined。你给它两个，它只会出一个。
然后老师为什么这个讲它比7不可以？
因为如果你选这两个的话，他们的 upper bound 是这三个嘛，所以你要在这三个里面选那个最小。
但是因为 f 肯定比 d 和 e 大，所以说 f 不可能。但是 d 和 e 里面又选不出来。
没错。
least
没错。
early order 的是在讲什么？
Early order 就是说你所有的都可以把它排列起来。
就像这样的，
没有这个还不能，你看 E 跟 G 还排不起来，
那就是一条直线是吗？
就是一条，它不是叫 chain 吗？记得吗？记得吗？
我搞忘那个在哪里。
记得吗？在上面吧。对，
先定值了。
OK，没有，我有写，我记得
这个
对啊，你看，你说是 call and chain，
就是一条线嘛。
对，因为所有的可以
整
那为什么 constructing Bayesian diagram 要这样画呢？
你想这样画还是这样画？
就是这是为什么 A B
它是从这个到这个。
呀，这个是最简化的，要画这个，这个是把所有 relation 都标出来。
它有一个步骤的，这个
对，
就先去除掉 loop，然后把这些 transitive 的也去掉，就剩一条直线，然后还要把直线去掉。
箭头去。
像一开始画，如果是画这种 diagram 的话，
呀，
是画这个 diagram 啦，我们要画出来，然后再
不用，直接画这个，最后一个，对，直接画最后一个，这个只是一个步骤吧，直接画最后一个。
就我们 list 出来，还有用那什么这些 list 体系的把 relation 弄出来。
就像我们那个 example，跟这个。OK。Okay. So, okay, before we go into minimization of gates, we should introduce few more terminology. So first, we will call it a literal And so this one will be very important. Later we'll keep using it to describe the algorithm. So first is literal. Okay, so what's literal? Literal is the complement or the Boolean a variable or the complement. Okay. So for example, x bar, y bar. Okay. So why we call it a literal? Because variable is just xy. Okay. But now we want to include the complement of x or y, or the complement of the variable. So we collectively call this thing literal. Okay. So these are literal. Literal can be complement of the variable or just the variable, the Boolean variable. Okay. Then next, we will define a min term or the minimum term. So the min term of the Boolean algebra, a Boolean variable, Boolean variable of Sn. Okay, so what's the min term? It's actually we want to care about the product of the literal. Okay, so it's actually a Boolean product where they are where yi are literal. Okay, so they can be si or si bar or together. They are literals. Okay, so in other words, a min term is a product of n. Okay, so for example, of min term would be like xy, xy bar, x bar y, something like that. Okay, so these are the min term. Yeah, makes sense. So this term will be created to describe algorithm. Okay. So next we're going to minimization of circuit. So we want to increase the efficiency of a circuit, or we can to reduce cost. Okay, because we use less circuit. So for example, you can see this xyz plus xy bar z. Okay, you can see that there are two min terms here, right? Okay, so they use 4 gates to build this circuit here. But if you go through the Boolean algebra identities here, okay, you can use the distributivity law to take out y plus y bar. And then y plus y bar is what? So if you imagine p or not p, what do you get? It's the tautology, which is 1. Okay, so 1 times anything is itself. So you can reduce to xz. So xz, you just use 1 and get, then you are done. So you can reduce 4 gates to 1 gate. So we will learn how to systematically reduce the gate. So first thing we need to do is define what the care map is. So let's define what's a care map. So the thing we learn is the Carnot map or the care map. Okay. So what's a care map? A care map is defined for a Boolean function. So let's say your Boolean function has n variables. Okay. Then we will need to construct 2 to the power n cell. So for example, if you have 2 variables, you have 4 cells. 3 variables, you have 8 cells. 4 variables, you have 16 cells. Okay, and so on. Where a 1 is placed in the cell representing a minterm if the minterm present in the expansion of the Boolean function. Okay. Before I give you the example, what about adjacent cell first? So cells are adjacent. If their minterm is differ by exactly one literal. Or that just now we said that minterm is a product of literals. So if two minterms differ in exactly one literal, then they are in the adjacent cell. Okay. So let's take an example here. Okay, so for example, we want to build a K-map for the following Boolean function here. Okay, so this Boolean function has how many variables? How many variables does this Boolean function have? How many variables? 2, x and y. Okay, so 2 variables, you have 2 to the power 2 cells. So you have 4 cells in total. So how do you build this cell here? So this cell should represent all the possible midterm. Okay, all the possible midterm. Okay, I put past the find the attendance of your friend because I need to find them from. Okay. Yeah. Okay. So this 4 cell will represent all the possibilities of midterm you can get. So for example, you will write you can label the cell like this. So the boxes here will represent xy, xy bar, x bar y, and x bar y bar. Okay. Okay, and then what you do is for this particular function here, if the minterm exists, you will put a 1 inside the box. So for example, if xy bar exists, you will put a 1 here. Okay. If x bar y exists, you can put a 1 here. X bar y bar exists, you will put a 1 here. Okay. So since there are 3 minterms here, you will have 3 1. Okay. Makes sense? Makes sense? Okay. So this is K-map. Okay. So for every Boolean function, you can build a K-map. Okay. And then you can see that these cells are adjacent. Okay. Because they are differ in exactly one literal. Okay. So you can see that this y, only y difference in y. Okay. For example, these two are adjacent because they are differ in x only, y is the same. And then these two are adjacent because differ in y, okay, because x, y is the same, and so on. Okay. So the position here we don't simply place when you get higher variable, this position will become more important. Can I show you now? Okay, maybe I'll show you later. Okay, let's look at 2 variables first. Okay, so first algorithm you will learn is called the K-map minimization method. So first, you have your Boolean function that you want to minimize. Okay, you can build a K-map for it. Okay, this works for n equals to 2, 3, 4, 5, 6, 7, and so on. But it will get harder when you go to higher variables. So second, what you do is you can identify the largest possible block. So this block here is not a special, it's a block of 2 power of 2n times 2 to the power n. Okay. Or n. What happened? No battery again. Okay. So you identify the largest possible block. Okay, this block can only be power of 2. Okay. So for example, 2 times 1, 2 times 4, 1 times 4, and then 2 times 2, or 4 times 4. Okay. For n times 2 power n. Okay. So what you need to do, you need to cover all the 1 in the Kmat using the previous block. Okay. And then use the largest block. So the min term can be combined based on the available block. Respond to the product form. Okay, so maybe sound a bit abstract. So maybe let's just see in 2 variables. Okay, so for example, in 2 variables, if let's say fxy equal to xy, so you only have 1 in 1 position here. Okay. So you only have 1 block, 1 times 1 to cover this one. Okay. So xy is already minimized. Okay. But let's say for example, your fxy is equal to xy plus x bar y here. Okay. So you will build a Kmat for it and then place 1 at xy and then place 1 in xy, x bar y. Okay. And then instead of forming 2 1 times 1 block, you can form a 2 times 1 block. Right? You need to form the largest block to cover the 1. But this block is power of 2. 2 to the power n times 2 to the power n. Okay. So in this case is 2. So you need to pick the largest block, cover the 1. Okay. So in this case here, once you cover here, okay, these 2 are adjacent, right? So this block actually reduced to y. Okay. Why? Don't know. Okay. Because you see, so from algebra sense, this will become x plus x bar times y. Okay. But what is P or not P? It's topology, right? So 1 times y, so it becomes y. Okay. So all the simplification is based on this logic here. Okay. So why we want to make them adjacent? Exactly because we can apply this kind of rule. So once they are adjacent, we can simplify one of the literal. So for example, here, this guy here. Okay, let's look at the second example. So this example is x bar y plus x bar y bar. Okay. So these are adjacent. They are differ in which literal? Y, right? Okay. So they are differ in y. Okay, they are adjacent. So you can apply the same game again. Okay. Simplify the y, and then you are left with x bar. Make sense? Okay. So these blocks here are created to simplify the sum of min terms. Okay. Okay. So why you can simplify, you can see from this algebra sense here. Okay. You combine the x and its complement. Make sense? Okay. Okay. Make sense? Okay. Okay. Next, for example, if we want to combine these 4 terms here, okay, we can build 2 times 2 block to cover them. Okay. 2 times. Okay. So you cover every one of them. And then these 4 actually equals to 1. Okay. Why equals to 1? Because you sum all the possibilities together. Okay. So you always get 1. If you don't believe, you can go and build the truth table for this function. Okay. So you will see that it actually always get 1. Okay. You can build the truth table for this. Otherwise, you also can see it from algebra. So for example, this is equal to x times y plus y bar plus x bar times y plus y bar, right? So you get x times 1 plus x bar times 1. And then you can reduce to 1. Okay. So you can do it from algebra. Okay. So yeah. So you can build see from algebra, or you can see from truth table as well. Okay. Build the truth table, you will see that you get 4, 1. Okay, next is this function here, x bar y plus x bar y bar plus xy bar. Okay, so you have 3, 1, 2, 3 midterms, so you get 3 ones here. Okay, so what kind of block you can draw? You can only draw the power of 2 blocks. Okay, 2 to the power n times 2 to the power n. So you cannot draw something like Tetris here. Okay, this block no use because you cannot simplify this kind of block. You only can simplify the adjacent one. Right? So in this case, we have 2 blocks to cover the one. Right? So the horizontal block will become the x bar, and then the vertical block will become the y bar. So this circuit, not circuit, this what? This function here can be minimized to x bar plus y bar. Okay. Any question? Maybe someone. Any question? Any question? Any question? No? Okay. So yeah. Okay. Maybe we see more for example. Okay. So in Excel, so blocks of 2 adjacent cells represent pair of midterms that can be combined into one term of one literal. So you can see that this adjacent cell, you make the sum of midterms that have 2 literal become 1 literal. Can you see? 2 literal become 1 literal. But here 2 literal become no literal. So if you have the block is larger block can reduce to less literal. So you can see that block of 4 cells here will become a product of no literal. You just get one. Okay. But just to note that this one is just for 2 variables. Okay. So let's look at the 3 variable case here. Okay. So in 3 variable case, okay, 2 adjacent cells will become a product of 2 literal. So just 2 adjacent cells will reduce 1 literal. Okay, so 3 literal become 2 literal. Okay, and 2 by 2 and 4 by 4 blocks, 4 by 1 block will become a 1 literal. Okay, and then block of all 8 cells will become a non-literal. So why there are 2 possible blocks here for 4 case? Because if you look at the 8 cell configuration, okay, how many ways to combine 4 cells? How many ways to combine 4 cells here? You can do a 2 by 2, or you can do a 1 by 4. So there are 2 ways to combine 4 cells in Excel. Okay. 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 So for example here, so let's say you want to combine X, x y bar z bar and x bar y bar z bar. Okay, so they are adjacent, right? So adjacent, they are differ by exactly one literal. So where's the difference? Where's the difference? X, right? Okay, so you can see that this x and x bar can be simplified. Okay, you can factorize it, simplify, and can see. Can see? Okay, so then you were left with two literal. Okay, so you reduce by one. So two adjacent cell, you can reduce literal by one. Okay, and then for example, this one here. So you got the x bar y z. Sorry, x bar y z is here, and then x bar y bar z is here. Okay, so these two are adjacent actually, right? Because they are differ by one literal. So they are differ in which literal? Y. Okay, so you can draw something like this. Okay, so like I said just now, the configuration become important here. So you cannot write y bar z here. Okay, you cannot switch these two. Okay, because these two are not adjacent. Right? How many literal they differ? Y z bar and y bar z. How many literal they differ? Huh? How many literal they differ? Y z bar and y bar z. Two, right? So they are not neighbor. So you cannot switch the position here. You cannot simply place the position here. You need to make sure they are all differ by one. Okay? And then the last one will differ by one again. So these two are adjacent, these two adjacent, these two adjacent, and then you will come back these two adjacent again. Okay, make sense? Okay, so you cannot simply place this link term here, otherwise the K-mat doesn't work. Okay. So in the C, if you combine the four terms here, you get Z bar. So you combine more literal at once, you reduce the literal more. So this one you left with one literal. Right. Just now you still have two literals. Now reduce two literals. Okay. Similarly, if you combine another four cells configuration, then you get one literal. And then if you combine all of them, that means you include all the possibilities. So you will always get one. It always happens because you include all the possibilities. Okay, makes sense. So similarly, you can do this for 16 cells. So 16 cells, you can imagine you got how many ways to build 4 or 8 cell map. Right. Yeah. Okay, any question on how to combine cells? Huh? Okay, next. Okay, because in 3 cells we might have some problem overlapping of blocks. So next we need to introduce these 3 words first. So first we call the implicant. So what's the implicant? Implicant is just the product of literal correspond to the block. Okay. So for example, just now, this guy SYZ bar, S bar Z, Z bar correspond to the blocks. Okay, are called implicants. Okay. So this product of literals we call it implicants. Okay, which correspond to the blocks of function being used. Okay, make sense? So we call this block implicants. Okay, the mean term that refer to this block, we call it the implicants. And then a prime implicant, okay, so prime number is used to build the number. So prime implicants here is if the block of 1 is not covered by a larger block. If the block of 1 is not covered by another larger block, we call the prime implicant. And then essential prime implicant is the only largest possible block that cover the one. Okay. So if this block of one is the only largest possible block of one that cover one in the camera. Okay, let's look at example here. Okay. So here. So you can see that all the product of literature that correspond to all this block are called the implicant. Okay. So now we need to decide what is prime implicants, what are essential prime implicants. Okay. So for example here, is this prime implicant? Why not? Why not? Huh? You mean this one here? This one here? Huh? Overlap? No, because although this one is overlap, but this one is not overlap. The bottom one is not overlap. Okay. So as long as this block of one is not contained in a larger block, then this is a prime implicant. Okay. Block of one contained in another block would mean something like this. Then this would become then this will be not an implicant. Okay. So for example, if I draw a purple, for example, if I draw one here, okay, this one is implicant, right? But this purple block is contained in a blue block. So the purple block is not implicant, not a prime implicant. Okay, so this is not a because it okay. This is not a prime implicant. So is this essential implicant? Let's go back to this blue. This is actually Y Z bar. So is Y bar Z bar an essential implicant? Essential implicants mean this block of one is the only largest possible block of one covering. Is the why not? Largest. There's only one way to cover these two these two, right? So this is also essential implicant. Essential prime. Okay. So for example, okay, next try another again. Okay. So let's look at D. Okay. So here have some interesting intersection here. So is the middle one a prime implicant? Yeah. Because this block of one is not contained in a larger block. Okay. So this is the prime implicant. So is this a essential implicant? Essential prime implicant? So you need to make sure that this block of one is the only largest possible block of one covering one in the camera. No, because this one here is covered by the other block. This one is covered by another block. Okay, so it's not essential. Okay. Makes sense. Just now one, although this one is covered by another block, but here no one covered this one. Okay, so this is still an essential block. Okay. So what we will, at the moment we will see why we call it essential. because they are exactly the one that we need to beat the minimization of the function. Okay. Okay. So let's look at this here. So let's look at these 4 examples here. Okay. So first you have 4 terms here. Okay. And then 5 terms. 1, 2, 3, 4, 5, 6, 7 terms, 4 terms. Okay. So correspondingly, you will plot 4 ones here, and then 5 1, and then 1, 2, 3, 4, 5, 6, 7 1 here, and then 4 ones here. Okay. So you build a care map, and then next task is you draw the block. Okay. Draw block to cover the 1. Okay. So you can draw 1 times 1 block, or 2 times 1 block, or 4 times 2 times 2 block, or 2 times 1 block, and so on. Okay, 4 times 1 block. Okay, make sure that the block you use are just 2 to the power m times 2 to the power n. Okay, these are the possible number you can use. Blocks you can use. Okay, and then for these blocks, you will minimize the min term here, simplify the min terms. Okay, so for example, let's go with this. So for example, here, this one, here is the most simplified form. Okay, so this one you cannot reduce anymore. But the adjacent one you can reduce, right? So this adjacent one you can reduce by 1 literal. Okay, so what you get is x z bar, because they differ in y. X y bar. You can combine them. Okay, and then the vertical one, they differ by what? Literal. X. Okay, so x can combine. So this block here will become y bar, z bar. Okay, so what you left with is s z bar, y bar, z bar, and x bar, y z. Okay, the one here. This one cannot simplify. Huh? The one here. Okay. 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 How about B? B. Okay. So B, you have 2 blocks to cover all the 1. Okay. So B, you have 2 blocks to cover all the 1. So this 2 times 2 blocks here, okay, you can reduce to just 1 literal. Okay. So this block here, you can reduce to y bar. Okay. Okay. And then this adjacent block here, you can reduce by 1 literal because they are differ by 1 literal, which is y bar, which is y. So this will become x bar z. Okay. So this block become x bar z. This block here become y bar. Okay. How many blocks will reflect how many min term you get in the simplified form? Okay. How about for C? C, you have 1, 2, and then 3 to cover the 1. Okay. So the horizontal block will reduce to x. Okay. And then this block here will reduce to y bar. And then the other block will reduce to z. Okay. Okay, D here a bit interesting. So D here got three block here. Okay. So which block do you pick? Do you need to pick all of them? No. Okay. So you don't need to pick all of them, right? To cover all the 1. So you only need to pick enough blocks to cover all the 1. Yeah. Okay. So let's say if you pick these two, is this enough? No, this is not enough because this is not covered. Okay. So you need to pick this one and the two horizontal one. Okay. So actually the vertical one is redundant. Okay. So you just need to pick this two is enough to cover all the one. Make sense? Okay. So if you pick these two will reduce to x z bar and x bar, y bar. Okay. Any question? Any question? No? Okay. Yeah. Okay. So first you need to form as many blocks as you can, and then next you need to use as fewer blocks as you can to cover all the one. Okay, this is the game for the camera. Okay. Any question? No? Yeah. Okay, next, in 4 variables, you can see that there are different ways you can combine 4 blocks. You can combine like this. You can also combine 4 blocks in this corner. These 4 corners are in adjacent. And combine 8 blocks differently. Okay. So similarly, in a 4-dimensional case, you also given a variables, you build the K-map first, okay? And then you try to draw all the possible largest 2 to the power of 2 blocks, product of power of 2 blocks, okay? So don't draw like 1 times 3. 1 times 3 cannot simplify. So only power of 2 blocks. Okay? So you draw all the possible power of 2 blocks. Okay? So you don't draw blocks like this, 3 times 1. Okay? You cannot simplify 3 times 1. You also cannot simplify, oh, no battery. So you also cannot simplify like something like Tetris. Okay. Tetris you also cannot simplify. Okay. Only power of 2 blocks. Okay. Yeah. So you can see that when the number of variables get larger, can the back hear me or not? Okay. So you can see that if the variable get larger, so the number of blocks you use will be higher. So for example, if in 5 variables you need to use 32 cells, 6 variable you need to use 64, and then 128. Okay, you can see that this cells will get larger. Okay. So next we will learn the Queen-McCluskey method. Okay. So this is for n greater than 4. So you don't need to deal with so many cells. But what you do is, first, you express each min term in the n variables by a bit string of length n. So you replace the x, y, z, the min term, with 1 or 0. Okay. So you put a 1 in the ith position for xi and 0 for xi bar. Okay. If x you put 1, x bar you put 0. Okay. And then next, you will combine the products, you will compute the products in n-1 variables that can be formed by taking the Boolean sum of min terms in the expansion represented by the big string that differ in exactly 1 position. So exactly is what we do just now. We combine the adjacent cell. Okay. So what you do is you combine all possible adjacent cells first. Okay, in this method. So similarly, you record it as 1 if xi occur, 0 xi bar occur. If the literal already get combined, you put that disappear already, that literal, so you put a dash there. Yeah. Next, then you keep continuing combining this Boolean product. So you keep reduce by 1, n minus 1, n minus 2, n minus 3, reduce until you cannot reduce anymore. Okay. And then you will find all the products, Boolean product that is not used to form new Boolean products. Then you will find the smaller set that represent the function. Okay. So let's look at the example. Okay. Look at the example. So for example, the example we're looking here is let me put here the record function. Okay, so the example here we're looking at is xyz plus xy bar z plus x bar yz plus x bar y bar z plus x bar y bar z bar. Okay, so there are 5 terms in this function here. So we want to minimize it. So first thing to do is you turn the min term into bit string first. Okay, so you can see that is if it is xyz, we put 1, 1, 1. Okay, x y bar z, we put 1, 0, 1. And then x bar y z, we put 0, 1, 1. Okay, so if you got bar, we put 0. If no bar, we put 1. Okay, so the game is like this. Then next, okay, step 1, what you do is you combine 2 adjacent cells. Okay, so for example, you see 1 and 2. 1 and 2 differ by what? Y. Right? So we can combine the Y. Okay. So we can simplify the Y and then the Y become a dash. Because we already simplified the Y. Y plus Y bar is 1, right? And then we simplify the Y. Make sense or not? Okay. And then you continue searching it. For example, 1 and 3. Okay. 1 and 3 differ by 1 literal. Where's the 1 literal? That they differ. X, correct? So 1 and 3 differ by X. So these 2 can combine, get simplified to YZ. So X disappears, so we put a dash. Yeah. So you keep doing it for 2, 4, 3, 4, and 4, 5. Okay. 4, 5 differ in Z, so Z disappear. Okay. So you can keep going on, and then you keep combining this adjacent 2 cell. So for example, 1, 2, and 3, 4. Okay. So what does it mean by 1, 2, 3, 4 here? So 1, 2, 3, 4 actually come from where? Let me see. Okay, actually come from here. Okay. So you can see that sz plus x bar z is equal to z, and then y bar yz plus y bar z is also equal to z. Can see or not? Can see? Can see? So this 1, 2, 3, 4 here actually refer to the 1, 2, 3, 4 here. Okay. It turns out that the first 4 here also use 1, 2, 3, 4 only. Okay. So the 1, 2, 3, 4 here refer to the original 1, 2, 3, 4. Okay. Make sense? Make sense? Okay. So now you can see that we can stop at start step 2 already because there's nothing more you can simplify it. Okay. So next step is to look for the Boolean term that is not used to combine, to form new Boolean term. Okay, you can see that actually these 2 are those Boolean term is not used because this 5 term is used to build the 5 terms here. Okay, and then the 4 terms here is used to build the Z here. Okay, so the unused Boolean product is these 2. Make sense? Make sense or not? Find the unused Boolean product. Make sense? Can I? Huh? Okay, because these 4 combines to Z already. Okay, and then these 5 terms combine to the 5 term here, and then these 4 terms get combined to 1 term here, and then so you are left with these 2 terms here. Okay. So next, what you do is you compare these 2 terms with the original function. Okay. So the original function contain 5 midterms, and then you left with two Boolean product. So you put a cross if the midterm here appear as a how to say? Okay, so you can see that how many midterms contain Z. Okay, if they contain Z, you can put a cross. Okay, so you can see that X, Y, Z contains Z, S, Y bar Z contains Z, X bar Y Z contains Z, X bar Y bar Z contains Z, but X bar Y bar Z bar doesn't contain Z. Okay, and then which midterm contain X bar Y bar, you also can put a cross. Okay. So you can see that these three doesn't contain X bar Y bar, but these two contain X bar Y bar. Okay. Okay. And then next, you need to find the set of midterm that think again. So how to say? You need to find the set of midterm. Okay. That make sure that you have an X. You have at least one X under. Okay. Let's back away. So how to say properly? Okay. You need a set of midterm that represent this function here. Okay. So to represent this function here, you need a cross, and you need at least one cross under each midterm. Okay. So you can see that after taking the sum of these two midterms, you can have a cross, at least one cross under each midterm. Make sense? Does it make sense? Does it make sense? Confused? Confused or not? Huh? Okay. Anyone confused? Anyone confused? No? Okay. If you're confused, you should ask. Okay. Confused? Maybe go through another example again. Okay. So let's say we want to simplify this function here. Okay. Let's simplify this function here. Okay. So we got how many midterms? 1, 2, 3, 4, 5, 6, 7. Okay. So we got 7 midterms here. Okay. We translate it into big string again. Okay. So you got a bar, you put a 0, and then so on. So they group by numbers of 1 so that they know easy to find which are adjacent to each other. Okay, easy to combine later. So next, you will combine terms, minimize term. Okay, so from these 7 terms here, you will form all possible simplification of the midterm, right? So for example, you can see that 1, 4 are adjacent. Okay, because they are differ in exactly one literal, which is x. Yeah, so you can get rid of x. And then 2, 4, they are differ in z, so you can get rid of z. Yeah, and so on. You can form all the possible way. Okay, and then next, you can combine the adjacent cell again. So for example, this one 3, 5, 6, 7 is coming from this one, this one, this one, this one. Okay, so this 4 can combine to W bar Z. Okay. Can see it? Can see it? Okay. So, okay. So how many unused Boolean product? So you got these 3 and this one is unused. because all the 7 terms here are used to build the Boolean product here, and then this 4 Boolean this 4 minterms here are used to build the Boolean product here. So there are 4 unused minterm here. Okay, and then take this 4 minterms, and then you put across if the minterms of the original function contains the simplified minterms here. Okay, so for example, you see which minterm contain w bar z. Okay, you can see that only this one contain w bar z. Okay, so this doesn't contain w bar z. And then similarly, you do for w y z bar. So w y z bar contains the minterm here, but it's not in here because here is z. Here also w bar and z. Here contains w y z bar. Okay, and then these 3 doesn't contain. Okay, and then you need to find the smallest set of simplified minterm here to cover all the minterms here. Okay, so for example, if you pick this one here, right, so you are uncovered for these 3 terms. Okay, so you just need to find enough terms to cover these 3 terms here. Okay, so you can see that if you pick this one, then you are left with this column here. Okay, so to cover this column here, you can either pick this or you pick this. Okay. So yeah, okay. Huh. I think most of you confused. Any question or no question? Okay, no question. Yeah, so if you pick 4 of these, will be too many, so you just need to pick 3 of them is enough to cover the original function, to represent the original function. Okay. Okay. So the function can be w bar z plus wyz bar plus ws bar y, or w bar z plus wyz bar plus x bar yz. Okay, so these are 2 equivalent functions that you can simplify the sum of these 7 terms. Okay. Okay. Yeah. Any question before we break? No. Where's the attendance list? Where's the attendance? Finish? Done? Done? Hey, why miss here? Okay. Okay. Who haven't signed the attendance? Okay. In this case, let's take a break until 10:55, and then we'll come back for quiz.没有这个哦，那你们的密室是得他搭过，没有人搭过，没有人搭过他，还是 not less than。好，那对，他没有人搭过。这样子，这个是没有 grade，没有 grade 的，因为如果这个点搭对面的话，就有 yes。那比如说这种，这个是 plan 的。Isomorphic 就是就是你要确保有一样的vertex有一样的，然后它们连接的方式也是一样的。谁还没有筛？你们 isomorphic 就是 道什么是 isomorphic graph？ 你们知道什么是 isomorphic graph 吗？不懂啊。isomorphic graph 就是如果两个 graph 是 isomorphic 的话，左边它们的 vertex 要一样。number of vertex 要一样，它们的 number of edges 也要一样。
一样
就是比如说就是 OK， 说如果你是要所以 isomorphic graph 就是说你要有一个 bijection between G 还是所以 bijection 就是说你有一个 function between vertex 和 edge， 所以你可以查前面如果这两个 vertex 连接的话，它后面那两个你 map 过去后那两个也可以。
就是它可能画法一样，但是这里是这个比如这样，比如说三角形，
比如说这个，比如说这个，有可能它一直变。
它这个图案就是擦掉。
比如说这个是 isomorphic 去。因为你只要送这一个点，这个点，这个。Elementary subdivision， 所以比如说这两条线是同一个 sequence of 对，这一条线透过这哪个点？
那三角形就可以画成。
因为我可以在 x 上面加一个点，
加多一个点。
对。
对，就是根据那个判断
是要求要有两上的 lower bound 它是有
也就是说，如果有一个的话，就是那个规则，或者有一个就是它就是那个。
就是如果它 lower bound 有一个的话，就是那个规定的
就是那一个。
通常 upper bound 也是。
呀，因为通常找不到是可能它有多过一个，但是最小的那两个比较最小那些。
比如说这个题
啊，对，
它这个一的我们有两，
对，这题有个让我
那就看这个吧，这个 BC 它有没有规？有就是 A 是不是？
有说，但是它有没有 lower upper bound？
对对对，
但是它有3个 upper bound， 但是
它不是 F 规，
最小的，对，
最小，
我们就大的里面最小。
没有，这只有一个也能用比较级，但是就是
对它的定义里面，
数都大于小于等于一个关。
这个考虑啊，这个它不两种，这是第二种
啊，对，
它是打算好还是只要会一种？还是比如说你这必须要写黄
对不同。先学。
这个最后的这个造成这个讨论的
因为我们要表一什么有个人问。对，你要说的你要找足够的名称来表达。我的表示对方针呢，只要确保每一个方针下面都有一个长。每一个名称的下面都有一个长。
这个比较去的。
OK。OK， 你看这个名称嘛，可以代表这4个名称。这4个名称被代表了，你还需要被代表。所以如果你选这个的话，那你就剩下这一个交代表，因为这2个的代表一个你的6个名称，对不对？然后你要。然后你还剩下这一个咯，对不对？剩下这一个的话，你可以有2个选择，你可以选这一个。
这否则这个底下都有一个好的不一定表示超的表述啊，只要每个项目都有的情况。
不可以选4个，因为4个就重复了。
要写最终的不是就是这3个或者是里面，但是是最终化解
不明白，很乱是不是？2半人。2个谁是2？
它跟它原本只是一个有三角形的这个
没有三角形，
对
能有三角形，那我出这个测试。
但是你要看他们不一样的我的地方，因为有时候它又符合这个哦，它符合这个我们就不能够讲它到底是对还是不对。对，看你哪一个，看你不符合。所以它哪一个好用，是看你的 graph 到底是符合或者不符合。如果它不符合这 equality， 你就要 make sure 它没有三角形哦，然后你才可以 deduce 它是 non-zero。但是如果它不符合这 equality， 你直接就可以 deduce 它是 non-zero。
那如果没有三角形，那我们可以
可以啊，
所以这
个比较简单，这个比较复杂。
OK，
因为6可以除法1嘛，不要被老师看。
其实不是要这么简单的，因为我们看其他的 example 那个错，它就放旁边一条，它
要拿进去，不用，对不对？
week 9的6去18那个
啊，
然后说27，因为这个旁边也是算 maximum right？
是，因为他没有人当过他。
对啊，其实我们不是看同一个 row， 我们是看每一个班级最高的那个就是
哎，然后那题也有算错嘛？
他是讲我其实他没有
那题也有算错嘛？
那个成就
哦，真的，我不知道他
是那个
也是可以的。
有错嘛？有东西有错嘛？
那可是
没有，
那两个人说这个都可以，看
就有个错嘛？
好像是 A 错吧？
就 A 错了，就有人提到这个东西。
改变最起码
对，我们全部都是做完。谢老师，这个情况不是。我一开始想的是，这个是 general 的情况，然后这个是如果没有三角形的时候，我才用这个圆圈，所以不是这样子的意思啊。
不，就是因为你只要不符合这个条件，你不符合 ，OK。现在是这样子，如果你要 prove something non-planar，不是，我是说这个比较好用，因为你只要 make sure 它把这个就好了，对吧 ？not 这个就 not 是了，但是你 not 是的话，你要确保它没有才可以证明这个，它可能只是说它有这个呢，它也会把那个。这边有2个情况你要确定，这边就直接推得出来。
这你有给一个 example， 他没有其他 condition， 他直接推翻那个
啊，对，
那个是什么情况？那是为什么会这为什么是这类？
因为他虽然讲是 lack of fit 啊，
可能它这个不符合它就是说它符合这个 equation， 我还是要符合。不符合的话就可以直接 not planar。这个是你可以算的东西吗？对不对？如果它符合这个条件的话，你不知道它 planar 不 planar。你看，知道是不是？
哦，
它不符合你才可以直接推。
的话，它也不一定是，
不一定。
它不符合，它一定不是。
因为这条线是从这里往这里对吗？所以 planar 的话，这个的话不一定的。
对，
感谢老师。
你看，刚刚那个刚好就有问题的。OK，对，因为你看，你只要选足够比较够的名称 that represent 这些function，每一个function下面，你只要保证有一个超，至少一个超的部分。比如说这个组上面，它 represent 这个是一个，那你现在3个名称你回答的，过后剩下这一个，这两个。东西的状况，你看，所以你看，这3个可以足够人的一个关系，就是说，这7个东西，这7个3，其实是等于变成减很大，全部这边全部都是在减段，这样，
谢谢老师。
Okay, let's start the quiz. So as usual, can I get the first person to count how many students in your row?你做到天不高。为什么还没？Okay, don't start first. So you can read. All right, your student name and student ID. Okay, so before we start, so the first page has 10 marks, second page has 10 marks, but got bonus question. Okay, so the bonus question only add to the second 10 mark. The bonus question only add to the second 10 mark. So the bonus question won't cover the first 10 mark. Okay, so split into two. Okay, if there's no problem, we should start 20 minutes. Let's see we can end at 11:25 or not. 3 more minutes. 3 more minutes. Okay, clean up your solution. I think about half an hour ago. Clean up your solution. Check your name, student ID. Okay, pass it to the front. Please pass your solution to the front. Oscar 会吗？有没有 Oscar？ Pass your solution to the front. Pass your solution to the front.他们里面好像没有哎，就我的 flag 有了，他们有没？他们有啊。可是他没有讲这个是二的，对，他不是二的，是二。没有是吧？没有，对了，啊，我还说过就是爱收东西还要买的，自己啊，哦，除了他，除了他自己，不一定，有的有情况可以同时。要 bonus 吧啊，这个是额外的分数吧。他就说啊，那个对啊，还要给额外分吧。拿了。我卖，他电坏了，要去换。电池坏。哎。买吧。 My battery got problem, so I need to go and change the battery. So you have any question on tutorial? No. If not, then we dismiss earlier today.
既可以按生活费又可以不没有费，那这样怎么办？